Okay, the following is a theory behind the magnetically induced spatial displacement drive, otherwise known as the warp drive. The idea is that it has to be faster than light, your inertia is relative to your reference frame, and it's completely electrically driven. This is not a new idea, and a lot of people already know how warp works, so I'll cut to the basics and tell you what I've added. So warp theory, for those who don't know, if you have an object moving through space, like in this example here, each one of these lines is 1 meter. It takes it 1 second to travel through all of them, so there's 7 meters. So relative to a non-moving object, they are traveling 7 meters per second. Alright? But with warp, you stretch the space out in front of you and compress it behind you. So you're traveling through less space at the same amount of time. So in this case, it takes me half a second because I've traveled through half the space because these are stretched out twice as much. Alright, so relative to a planet or whatever, my velocity is going to be 14 meters per second. Relative to me, I'm only traveling 7 meters per second. So there is a spatial differential of 2 to 1. How do you get that? Flux density is what we need. Basically, magnetic fields flatten space. Typical electromagnetic coils can only do so much. Even our best superconductors, when you have a coil, even though it's hard to see that in this bad drawing, but a coil of wire or a coil of anything that's conductive, and you pass an electrical current through it, what it's going to do is it's going to create a magnetic field as such, and your flux density, even though it can be quite strong, is nowhere near what we're going to need. So your best bet for creating the maximum flux density is what I call a free electron helix. That's basically where you shoot free electrons into a spiral pattern, and if it's in a vacuum, a complete vacuum, which yes, I know complete vacuum can exist, but anyway, they have almost no basically no resistance. You just push them away from the walls of the container using electrical fields of the same polarity, and you push them forward at an angle, and they will spiral, and you will create one heck of a magnetic field, the best you can possibly get. This would be powered by something like, say, antimatter reactor. Alright, now on to the warp factor. This is where I am going to tick off a lot of the Trekkies. Instead of having warp be a specific speed, I'm having it be a multiplier that is in reference to your spatial differentials. So in this case, warp 1 gives you a 10 to 1 ratio. So if you're traveling, let's say, 874 times the speed of sound, real fast, right? At warp 1, you have a 10 to 1 multiplier, and that means you're now traveling relative speed, 1/100th the speed of light. Relative to you, you're only traveling 874 times the speed of sound. So how you would describe that is here, 1e1. So that basically means whatever the value is over here, in this case 1, times 10 to the power of 1. So your warp is going to be this last number here, as you can see. Alright, so now you get up faster and faster. You get like warp 9 in this case. You can see it adds up quickly. Not only does your speed function as a multiplier, your acceleration does as well, which brings me to why I want warp factor to be in this format. It is because of split G acceleration. Instead of having a power source that's constantly pulling you down, trying to keep you like some sort of gravity plating or whatever they have in Star Trek, or having like a spinning wheel or anything of that nature, I say instead you take the ship, instead of moving this way towards your destination, you move upward. In fact, you continuously accelerate by using, let's just say, impulse drive, which is an electrically driven inertial transfer engine. And you're accelerating at a rate that is exactly equal to what you would experience on Earth, which is 1 gangster. That's what the G means. Alright, so you have a entrance velocity, which you always have to be moving to start this anyway, so I'm having it at 9.80, blah, blah, blah. You see that. Alright, so you're going to go between you and the destination. You're going to accelerate at 1 gangster all the way to the midway point between you and the destination. At that point, the ship will invert, or craft, or whatever, and you'll start braking at the exact same deceleration rate. So the entire time, if you're very careful, you could be experiencing 1G the entire time. In fact, if you left the planet at a specific angle and orbited at a certain rate, you could go from Earth all the way to wherever your destination is without ever losing the loss or ever losing gravity relative to you, of course. So I say everything should be a 3-day trip minimum. Why 3 days? If you ever try to pick a point very far away in space, like in space simulators, and go to it, you'll notice that when you actually, no matter how accurate you think you are, when you actually get close to that point, you're very far away. Just a fraction of a degree of difference means you can be, several million kilometers away. So what you want to do is be able to make corrections the entire time. It also helps with adapting, like say you're going to a place where the gravity is different. You can adapt to the gravity of your destination by changing your acceleration and deceleration rate, and it would be not as much of a shock to your system. It's just important to remember to invert the craft midway and start the braking. You could also adapt to, let's say, the day and night time of wherever it is you're going, reduce jet lag, whatever. Anyway, so that leads to the last part, which is the spatial differential calculations. So here we got a couple of destinations. Pluto's lovely this time of year. The planet Pluto. Vega, pretty far away. It's a star system. Sagittarius is a galaxy, if you can call it that. It's kind of connected to ours. It's like offset down and to the left a little if you're looking at the center. Andromeda, really far away, blah, blah, blah. Alright, so the trip time we say is 3 days. Our acceleration matches what we have on Earth, so you feel 1 gangster of gravity. Your initial velocity is the same as, well, I shouldn't say the same, but acceleration time, half of your trip time in seconds. Alright? And we set that. We set it to what we want it to be. So we say the total distance we're traveling to Vega in this example, our total distance, 25 light years, converted into meters and cut in half is our midway distance. And that is also going to be the distance that we're going to accelerate for. Now, our warp acceleration that we'll need in order to make that trek in the amount of time that we have, or make half that trek in half the amount of time, is calculated here. I take the normal formula for calculating distance traveled with acceleration, time, and initial velocity, and I reworked it so that you can tell what the acceleration has to be, given those values, and in this example, our acceleration is here. Alright, so then we have to calculate what our spatial differential is, which is here. You take that acceleration value that you just did and divide it by your local acceleration. So you're only going to be experiencing 1 gangster of gravity, and in reality with that level of spatial differential, which is 1.44 warp 6, you're actually going to be traveling at a rate, or acceleration, and that is about it. There are, however, some design considerations. For instance, you're going to be experiencing dust and things in space. That has to be dealt with. Not entirely sure, because a tiny speck of basically anything, even at that relative velocity, even at the local velocity, can do quite a bit of damage if it impacts the hull. So that you need to take in consideration. Also, there is going to be, at extreme velocities, even in space, you're going to start to experience drag. Because space is not actually a complete vacuum. There's gas out there. It's few and far between and somewhere, but it's out there. So that is going to limit your acceleration, at least your local acceleration. Let's see, other things are your magnetic field should always be contained to the outer hull and never go through the inside. If you think about what that would do to something on the inside of the ship, if it can bend or flatten space that much, yeah, you don't want that on the inside. Also, considering you are stretching space in front of you and compressing it behind you, you will more than likely have to have an asymmetric magnetic field. And that is about it.